continue with some alternatives to CMOS. This first one we'll look at is called clock CMOS or C-squared MOS. And basically we're moving toward a dynamic logic, and that means it's not static, which basically means it's not operable at DC. So you need a clock for these circuits. So the C-squared MOS gate is a modification to the basic static CMOS gate. There's not much of a modification. It displaces two transistors that will isolate the pull-up and pull-down sections from the output. And so basically here's a schematic of it. This is our old PMOS logic block and the complementary NMOS logic block, and this is the logic function, whatever happened to be there. And when phi is equal to 1, so phi is equal to 1, phi bar is equal to 0, these two are both on, and it operates as normal. When phi is equal to 0, then we basically isolate the output from the NMOS logic and the PMOS logic blocks. So it forces the value on the output to remain constant even if the input transitions occur. So we may also see this if you're trying to put something into high impedance. So this is this little discussion talking about the number of transistors. Basically, it took 2n plus 1 transistors. The equations kind of would represent the n for the pull-down section and the n in the complementary pull-up section, and then 1 for the clock for both one of P type, one of N type. So moving along a little bit, we're going to look at some dynamic CMOS, and what that means is that the state and the charge for that matter is stored on the capacitor, and again it also won't run at DC. That's where the word dynamic comes from. So the dynamic logic operates in two distinct phases governed by a clock. As we know, static CMOS logic uses pull-up and pull-down sections which operate concurrently at the same time. The dynamic logic phases typically operate in two distinct phases, and they're denoted pre-charge and evaluate. So here's a simple example of a schematic of a NMOS logic and a dynamic gate. So in this particular case, phi equals 0. This is pre-charged. So if phi is 0, this guy down here is off. This guy's on hard, and it's pulling the output out to VDD. So that's what the P stage is, or the pre-charge stage is. You put something into a known state. In this particular case, we're storing rather VDD on this output capacitor. And then what happens during the conditional discharge? Well, this P-type transistor now, since phi is equal to 1, this is off, right? And basically we would just have this little section down here to worry about with this N-type transistor on. So whatever the NMOS logic happens to be will, conditionally discharge that output capacitor. So that's the way that tends to work. If this NMOS logic gives a conducting path from the output to ground, it'll discharge the capacitor. If there's not a conducting path to ground, it won't discharge that capacitor. And that's known as the evaluate stage. So most of this you don't need to know, but this basic idea of the pre-charge and evaluate is fairly common and quite important. And then to some of the trade-offs here, like leakage current and whatnot that could occur. Clock frequency too slow, may degrade the charge on the capacitor. And here's a simple example that sort of shows some of the issues with these types of gates. In the first case here, we go through a pre-charge and then an evaluation phase. Everything's sort of working as normal. And then there's a pre-charge and then an evaluation where there was simultaneous occurrences of ones on these inputs to A and B, and would have, erroneously discharged some of the charge from that capacitor. So that just points out that there's some issues with dynamic logic design that have to be taken into account. And so one of the main rules that comes out of this, if you're using that type of structure that we're looking at here, is that you try to make a rule so that only 0 to 1 transitions on input signals could occur on the NMOS block. And that'll lead to another slight evolution to the dynamic logic gate. There's also some charge sharing problems that you might anticipate. And all that really means is that, like, every node in this circuit here has a capacitor associated with it, but there's a potential situation in which, you may end up having initially pre-charged this output capacitance to 1. This guy here would have potentially could have been at 0 before. These can still be off. This guy could come on, and then charge would be shared between these two capacitors. So the output effectively would be reduced in voltage. And this is a simple little example of what may happen if you did some charge sharing. So the point is, again, that you'd have to be aware that those things could occur and perhaps potentially design for them. So charge sharing can be an issue, and we'll look at that a little bit later when we look at memory, in particular charge sharing that occurs when we want to sense the voltage which might have been on a DRAM capacitor. So that effect is known as charge sharing or charge redistribution, and may have to be accounted for. Certainly, if you're building these types of gates, it would definitely have to be worried about. But typically, it's going to be buried in some embedded memory or something, which may or may not be an issue that you'd have to worry about. Here's one little scenario that might prevent some charge sharing or some circuit technique that you could use. And this is just to on the output put a weak pull-up device here. So this is similar to that pseudo NMOS that we saw earlier. Pre-charge would evaluate this. There might be some charge redistribution, but this would replenish some of the charge on that output node. So this replenishing current, would limit the clock period, but it would eventually drive the output high. The technique is applicable with any type of dynamic gate, and we'll look at something like that when we do look at DRAM in a fair bit of detail, because what happens there is we end up, perturbing the charge which is on the capacitor of the memory cell, and basically we have to replenish it. So those basic ideas are quite common, but you're not going to really encounter them in these types of gates. And at this point in time, we'll take a brief break.